Thank you for inviting me to this forum. My name is Arun Majumdar. I'm a professor at Stanford University and also the Dean of the new Stanford Doerr School of Sustainability. This is the first school Stanford has launched in 75 years on addressing arguably the defining issue of the 21st century, climate and sustainability. It took about 1 million years for the world population to grow to 300 million, which is roughly the population of the United States. And today it takes 13 years to add 1 billion. We are at 8 billion people in the world. By 2050, it'll be 10 billion, and 2100, which is the time frame of our grandkids, it'll be 11 billion, plus minus 1 billion. That's the uncertainty. I call this the human tsunami. The world has never seen, the earth has never seen anything like this before. In addition to the human tsunami, there are a few others. There's the human consumption tsunami. The outer curve out here is the per capita GDP, which has gone up exponentially. And if you take the per capita GDP and multiply it by the population, you get the total GDP. And these are all super exponential curves. And while this has led to prosperity, it has improved the quality of life, it has consequences. I talk about consumption tsunami, and yet I'm presenting GDP, which is about products, production. And that is because people are producing, because humans are consuming. And to produce these things, we need energy. And here I'm only presenting 4 generations of my own family. I was born in the 1960s. My children were born in the 1990s. My parents were born in the 1920s and 30s, grandparents in the turn of the century. In a matter of 4 generations, we have completely transformed the way we use energy from mostly traditional biomass to mostly fossil-based energy. And this is on a longer time scale, this is a super exponential also. I call it the energy consumption tsunami, to make the products and goods and services to feed and to provide for the human tsunami. And it is not surprising that with the energy consumption tsunami, we have a CO2 tsunami. There's a water consumption tsunami, there's a plastic tsunami, and you can go on and on. That's the world where we are in today. And a lot of people feel that this is unsustainable. But it has led to amazing quality of life. We have this world today where we live in electrically lit and air-conditioned homes. Not everyone around the world, but a large fraction. We have information on our fingertips. We sit in our homes and watch television. Our life expectancy has doubled, more than doubled. We have transportation like we had never before, international trade, mobility. We can go around the world in a matter of few hours that used to take more than months. And we have just amazing healthcare that 100 years ago was not around. This all happened in the last 100 years of development, and it has completely transformed human life. So let me give you a quiz. There's a consequence of this which appears in some numbers. I'm going to throw some numbers at you. 1, 2, 800, 40, and 20. And I'd like you to think about what these numbers mean. The first one is 1 degree Celsius. This is roughly the temperature, the global average temperature rise from the pre-industrial level is about 1.2 degrees, but I've just made it to 1 degree. This is the global average temperature rise due to CO2, due to global warming. The next number is 2. It's 2 degrees Celsius. That is the Paris Agreement in 2015. And the agreement is, it was an acknowledgement of the problem, and the world agreed that they'll do whatever it can to keep the temperatures below the global average temperature rise below 2 degrees Celsius. The next number is 800. If the temperature needs to be kept below 2 degrees Celsius, we have a budget, a global budget of 800 billion tons of CO2 left, 800 gigatons of CO2. The next number is 40. This is the rate of CO2 emissions per year. It's 40 gigatons, 40 billion tons of CO2 per year, globally. The last number is 20. If you're emitting at 40 gigatons a year, and you got 800 gigatons of budget, we have 20 years left. That's the urgency of the problem. And while we talk about global averages, the averages don't matter as much. What matters is the distribution. I can say I can put my head in the refrigerator and put my legs in the microwave oven, and my average would be great, but the tails are in really bad shape. So it's important to understand what these tails mean. This is data from NASA over from the 50s and 60s of summer temperatures. Some summers are hotter, some summers are cooler. Cooler summers are blue, hotter summers are red. But over time, from the 50s and 60s to 70s and 80s and 90s and now, you find that distribution is going to the right. The probability of having extreme summers, extreme weather, is just increasing by a factor of 10 to 100 in many parts of the world. And this tail of the distribution has disproportionate effect on our economies, on our human life. And this is what you get to see in wildfires and droughts and flooding and coastal inundation and extreme heat. And this is only going to get worse. And this is why, even though we talk about 1 or 2 degrees, it is really a manifestation, a reflection on the tail of the distribution. So this is the problem that we are running into. People have realized this problem. Nations, countries have realized this problem. And in COP26 in Glasgow, many countries made commitments. The United States made a commitment to become a net zero economy by 2050. China is in 2060, India is 2070, and you can go down the list. Japan is 2050, Germany 2045, and you can go down the list, and everyone made a commitment. And it's not only countries. More than 60% of the Fortune 500 companies have made climate commitments. And their aggregate annual revenue is $20 trillion, the size of the US economy. So nations have made commitments. Large businesses have made commitments. And if you ask the question, do they know how to get there to meet the commitments? The answer is no. No one really knows how to meet those commitments yet. So this is an amazing time in history where everyone is aligned to do something, but no one exactly knows how to go about doing it. That's the world we are in right now. And it is not just the large corporations and government. Consumers, especially the younger generation, have realized. This is some data on consumer demand on sustainable products. And 77% of the consumers are willing to pay a little bit of a premium for brands that offer clean products. These are Gen X, millennials, and Gen Zs. And it's not just in the United States and UK. This is global. And this is just Google searches on sustainable products. So we are somewhat of a tipping point. The question is, what do we do about it? Here's a chart. On the vertical axis is the rate of emissions in gigatons of CO2 per year, CO2 equivalent per year. On the x-axis is time. And the business as usual is the yellow curve up there. And if you are to keep our temperature rise below 2 degrees, that's the red curve. So you have a huge amount of mitigation to be done on the order of 30 to 40, 50 gigatons of CO2 per year. That's just reduction of emissions. But that's not enough. You have to do more. And that's the blue in the negative side. This is negative emissions. This is pulling out CO2 from the atmosphere at the rate of about 10 gigatons of CO2 per year by about 2040, 2050 or so. And so the reason being, the lifetime of a CO2 molecule in the atmosphere is several hundred years. So the CO2 emissions that happen by burning coal in James Watt steam engine in the 1700s, 1800s, those CO2 molecules are still circulating in the atmosphere. And so the atmosphere is like a large capacitor that accumulates CO2 that have been emitted. We have to take that CO2 out of the atmosphere, and that's your negative emissions. So it's not either or, but it's and. Both have to be done. Now, we're talking about tens of gigatons of CO2 as if they are numbers. Let me give you a comparison of what that really means. If you add up the weight of all 8 billion human beings on Earth, and you ask the question, how much is that in gigatons? And the answer is, it's half a gigaton. All 8 billion human beings, total weight, half a gigaton. And we have been asked to remove tens of gigatons of CO2 from the atmosphere and reduce the emissions by about 50 to 60 gigatons of CO2. That's the challenge in front of us. This is nothing short of a new industrial revolution, which is an enormous challenge, but it's also an opportunity. I would also pose that whatever 10 billion people consume will have a gigaton scale impact. This is electricity, heating and cooling, transportation, food, textiles, water, steel, cement, information, and so on and so forth. And so all of these industries, all of these sectors have to change to meet the climate goals that are set forth by the alignment of nations as well as businesses and population in general. And if this is not the biggest opportunity, business opportunity, I don't know what is. All these industries have to change. That's why I say this is the defining challenge and the opportunity of the 21st century. And I just talked a little bit about the energy part, and I'll talk a little bit about the others. Energy is not independent. Energy, what happens in energy affects water. What happens in water affects food. What happens in food affects biodiversity, ecology, global health. And all of them are impacted by climate change. Climate change is an underlying thing that impacts all of these different sectors. And that's why this becomes the defining challenge and the opportunity of the 21st century. And it is very hard to look at energy separately from water, from food, etc. They're all interrelated. This is not just a science and engineering issue or a business issue or law issue. This is all of the above, which makes it a uniquely 21st century problem. So at Stanford, we have been around for 130 years or so. We are divided into 6 schools: School of Engineering, Graduate School of Business, School of Medicine, School of Law, School of Humanities and Sciences, and Graduate School of Education. And we used to have a School of Earth, which we ended, and instead, in addition, we launched the Stanford Door School of Sustainability to bring the whole ecosystem of Stanford and Silicon Valley to lean into this effort. We are, as you may well know, we are in the middle of Silicon Valley. In fact, Silicon Valley started here at Stanford and then spread. And the impact of that is not only just local, but global. We are now taking that same approach or similar approach and saying, what can we do globally on the sustainability front, given that this is the biggest challenge and the opportunity of this century? In many ways, we have to reimagine academia. This is the first school Stanford has launched in 75 years. And we are trying to create a future in which humans and nature thrive in concert and in perpetuity. This is about knowledge, this is about education, and this is about solutions. And we have to reimagine academia because academia, as I pointed out, we have structured academia with School of Business, School of Law, School of Engineering, School of Sciences, but sustainability transcends all of them. So the Door School of Sustainability has to be connected to all of them. It's an all-campus effort, but we have a school. I call it a three-legged stool. And the first leg is tradition. We have departments where we hire faculty, where we admit students, we grant degrees, we create curricula, and we have discovery research, curiosity-driven research, which is very important. We have just launched a new department on oceans, very important. And we have departments in sciences and engineering, as well in social sciences, in economics, in global environmental policy, environmental behavioral science. These are social science efforts because it has to span the gamut of human experience from science to social science and humanities. This is traditional school. In addition to tradition, the second leg is a break from tradition. About 15 or 20 years ago, we created institutes at Stanford, which are cross-cutting. The Woods Institute for the Environment, the Precourt Institute for Energy. And what they have done over the last 15 or 20 years is to create a connective tissue across our whole campus, bring students and faculty and staff together, and do user-inspired research to prove a concept of breakthrough ideas. And they've done extremely well. They've formed a connective tissue not only within campus, but also with the outside world. And these institutes have now come within the school to give it the porosity and the connective tissue that a school like this badly needs because it cannot be siloed out. While these two are really important, there's a third leg, and that is a new effort called the Accelerator. This is about impact at speed and scale, to use the words of John Doerr in his book. And this is about scalability. While proof of concept research is very important for breakthrough ideas, if these ideas don't scale, they don't matter as far as impact on climate and sustainability is concerned. And so the proof of scalability is a very important factor, and that's the goal of the Accelerator. And I'll talk a little bit more about that. But just to give you an excitement of where we are, so this is the Accelerator. In Stanford, we have faculty, students, postdoc staff. And it's very important to understand what does scale mean and what kind of solutions are we looking for. We are looking for big problems in the world. So we are looking for what we call flagship destinations in long duration storage for the grid, negative emissions that I talked about before, hydrogen at scale, a measurement system of climate relevant information, conservation, fresh water production, net zero emissions steel and cement and chemicals, net zero emissions fuel, food productivity. These are all examples of themes of flagship destinations. Note, just to take the first one, the storage, it has to be, if you really want to solve the problem of the world, this has to be at the 100 terawatt hour scale at a very low cost. This is equivalent to President Kennedy in 1962 saying that we'll go to the moon and return safely within a decade. That was a flagship destination, which we often call the moonshot. Here's an example of a whole bunch of them. Now, it was easier said than done to actually put a flagship destination of going to the moon. What was needed was much more. To actually get there was a really hard problem. They had to do many things together. They had to develop rockets. They had to develop propellants. They had to develop a navigation system, a spacesuit. All of that had to come together within the decade. And so the same thing happens out here. For each of these examples, there are multiple problems to be solved and all brought together. And this cannot be done alone. A university cannot do this alone. We need partners, external partners, businesses, governments, nonprofits. And the pathways are different. It could be a commercialization, technology, products, commercialization. It could be a policy lever to really make that impact. could be a digital platform for the ecosystem to share the data, or it could be an education and mobilization, or a combination of all of them to get there. So we are launching this right now. We have launched it to partner with folks around the world to see how we could jointly, collectively get there, because Stanford alone cannot really get there alone. But it's very important to understand the scale, because if you understand the process and the pathways to get to the scale, we can go back and identify the right problems to solve, which, if solved, can be rapidly scaled up and get to the flagship destination. So this is a reimagination of an academic institution. And we haven't quite tried this in the past. And this is we feel is very, very important to show proof of scalability. That's the accelerator. So we have had some breakthroughs in the past at scale. We have had a lot of natural gas. But if you look at renewables, they started about 30 years ago, 40 years ago, whether it's solar photovoltaics or wind, and it took about 30 to 40 years for it to come down in cost and get to scale. We don't have 30 or 40 years. So the question is, how can we accelerate? And today, solar and wind are the cheapest way to produce electricity. The same thing happened with lithium-ion batteries. 10 or 15 years ago, no one could imagine that the lithium-ion batteries could come down in cost. And we are at the verge. In the next few years, the lithium-ion battery cost will reach $100 a kilowatt hour. And when that happens, electric vehicles become range competitive and cost competitive with gasoline cars. So it's not a surprise that most of the auto companies are now pivoting towards making electric vehicles now. And many are saying they're not going to make internal combustion engine cars after 2025 or 2030, 2035, etc. This is a tectonic shift in the industry. But it took about 30 years for the battery cost to come down. We don't have 30 years. We got to accelerate. The same thing with LED lighting. And I can go on and on. But these are some of the good news stories. But that's not enough. This is very optimistic. I want to give you the optimistic picture, but we need much more. To really want to address the climate change, we need much more. Well, as I said, we need multi-day grid-scale storage. We may need, in many places of the world, small modular reactors at very low cost. Refrigerants are a major greenhouse gas. They need to be replaced. Buildings consume a lot of energy. They also leak. So zero net energy building and zero net cost would be terrific. Industrial decarbonization is probably one of the most difficult. Hydrogen may be needed. This is steel, cement, petrochemical. And decarbonizing food and agriculture, which is the source of about 25% of global emissions, is from a food sector. And as I pointed out, we need a massive gigaton scale carbon management where we suck out CO2 from the atmosphere. All of this is needed. And each one of them is $1 trillion industry, and that has not yet started. That's the opportunity, the biggest opportunity of the 21st century. We're starting a little bit. These are some examples of grid-scale storage. This came out from Professor Yi Wei, one of my colleagues, and this is an Enervenue. It's a very interesting storage solution that is scalable because these are widely available materials. It is cheap, and they are developing this technology right now, spun off a company, and they're trying to scale. In the hydrogen world, there are 3 companies that have been launched by Stanford. The most evolved one is monolith materials. These are methane pyrolysis. The other one is Molten, which is also methane pyrolysis. And the third one is Evolo, which is a very novel electrolyzer company with alkaline electrolyzer by student Jimmy Rojas. And so this is just a few examples of things that have been spun out that are in the process of scaling. And there's plenty more that are happening. Not all of them will be successful. But the point is that this is the start of an entirely new industrial revolution that is starting out here. Let me end with a quote, an indigenous people's quote, which is painted on my office walls. And it gives you an idea, it gives you a different perspective how to look at the future. And the quote goes as follows: "We do not inherit this earth from our ancestors. We borrow it from our children. What we do today is really going to affect our children, grandchildren, or the world in the future."